Okay, so imagine for a second you're standing in the middle of the absolute darkest place on Earth.
Right.
Maybe the Australian outback or the middle of the Pacific Ocean. You look up and, depending on how good your eyes are, you see a few thousand stars.
Yeah.
Feels like a lot.
Oh, it feels crowded.
It feels crowded.
It's a beautiful sight.
Yeah,
But in the grand scheme of things, what you're seeing is, well, it's barely a rounding error.
exactly. We know the observable universe has millions of billions of stars. The numbers get so big they actually stop making sense to the human brain.
They really do.
And thanks to missions like Kepler, we now know that planets aren't some, rare freak accident. It's the norm. Statistically, there should be billions of habitable planets out there.
It really is just a numbers game.
Yeah.
Even if intelligent life is incredibly rare, the sheer scale of the cosmos means civilizations should just be possible. They should be abundant. We should be bumping into them.
And yet,
And
nothing. Absolute silence. We point our radio telescopes at the sky. We've been doing it for decades, listening for signals, for patterns, for anything that sounds like a hello.
and all we get back is static.
Yeah.
Just the cosmic background hiss. It's the ultimate ghost town.
And this brings us to the Fermi paradox. I think most people have heard of it, but it's worth restating because the math makes it so incredibly frustrating. If the universe is this old and this big, where is everybody?
It feels like walking into Times Square on New Year's Eve and being the only person there.
That is a haunting image.
And it's the question that has driven astronomers, philosophers, everyone up the wall for 70 years. Usually the conversation ends up at the Great Filter.
Right, the idea that civilizations inevitably kill themselves off with nukes or climate change before they can make a phone call, which is the depressing answer.
Everyone is dead. Great. It is the depressing answer. But today,
Yeah.
today we're going to look at something different, something that suggests we might be looking at the problem completely backwards.
Oh.
What if there is no filter? What if the galaxy is actually incredibly noisy, shouting at the top of its lungs? But we're just deaf.
Deaf. Or just tuned to the wrong station.
Worse. The theory we're diving into today suggests we're the cosmic equivalent of someone trying to pick up a high-speed Wi-Fi signal using a ham radio.
We're looking for smoke signals in the age of fiber optics.
Precisely. And the culprit here, the thing standing between us and first contact, might be quantum mechanics. Or, I should say, our lack of mastery over it.
So the theory is that aliens might be talking right past us, using physics we're only just beginning to get our heads around.
Specifically, quantum communication. It's a field that's exploding in our own labs right now, but when you apply it to a galactic scale, it changes all the rules of the game.
So let's unpack this. Why would aliens ditch radio waves? I mean, radio is reliable, it's easy. Why make things complicated with quantum physics?
Well, to understand that, you have to look at the practical struggles of just talking between stars. The biggest hurdle isn't tech, it's astrogeography. The distances are just unimaginably vast.
Right. Even at the speed of light, a message to our nearest neighbor, Alpha Centauri, takes over 4 years to get there.
Exactly. And that's just next door. Across the galaxy, you're talking tens of thousands of years.
So you can't have a conversation. You say hello, and 10 years later, best case, you hear hi.
It's the ultimate lag. But here's the real nightmare scenario. What if the signal drops? Imagine waiting 10 years for a reply, and all you get is,
Sorry, you cut out. Can you repeat that?
yes. That's another decade or two of your life just wasted. Time is the most expensive commodity you have. You can't afford to be inefficient.
So you don't want to chat. You want a data dump.
You need to send as much information as possible, as reliably as possible in a single go. And this is where quantum communication, or QC, comes in. It is just incredibly more information dense than radio or lasers.
Okay, lay it on me. How much better are we talking?
It's a fundamental shift. Let's start with a protocol called super dense coding. In a classical computer, a bit is a 1 or a 0.
Binary.
But in the quantum world, we use qubits, which can be in multiple states at once. With superdense coding, a single qubit can transmit 2 classical bits of information.
Oh, okay. So it's a two-for-one deal. You send one particle, you get double the data.
It's a 2x speed up right out of the gate. But that's just the appetizer. It gets even more extreme with something called the hidden matching problem.
That sounds like a Robert Ludlum novel.
It does, doesn't it? But in this context, it refers to a certain type of complex communication task. I won't bore you with the math, but basically, for some jobs, using classical bits requires exponentially more data than using qubits.
So we're not talking double the efficiency anymore.
We're talking orders of magnitude. So if you're a civilization building a galactic internet and you have the choice between a system that needs a billion bits or one that needs a few dozen qubits to do the same job.
You're going with the quantum option every single time. It's a bandwidth issue.
Exactly. Not to mention, QC allows for levels of security and computation that are physically impossible with classical means. It's just the logical next step.
And I feel like but coming physics always charges a toll, doesn't it?
There is always a toll. And this is where we have to get really specific.
Let's hear it. What's the catch?
The catch is entanglement. For something like superdense coding to work, the receiver needs to have what's called a pre-entangled qubit already in their possession.
Wait, hold on. Run that by me again.
To receive the message efficiently, you need to already have the key.
If I have to physically send you a key before I can send the message, doesn't that defeat the purpose? If I have to fly to Alpha Centauri to give them the key, why not just deliver the message while I'm there?
That is a fantastic point, and it's the biggest criticism people have when they first hear this. It sounds inefficient, but think about it in terms of infrastructure. Think about laying fiber optic cables on Earth.
Okay.
It takes months, maybe years to lay a cable across the Atlantic. It's slow, it's expensive. But once that cable is laid...
You have instant, massive data transfer.
Exactly. The pre-entangled key is the cable. An advanced civilization isn't flying to Alpha Centauri just to say hi. They're sending out automated probes to every star system in their neighborhood.
Carrying banks of these entangled keys.
Yes, they drop them off, set up a repeater, and move on. It's an investment.
You're not building the internet for the first email. You're building it for the billions that come after.
It's the ultimate infrastructure project. So let's assume they're doing this. They have this amazing quantum internet buzzing across the galaxy.
Here's the pivotal question then. Even if they're using quantum tech, why can't we just hear it? A photon is a photon, right? Shouldn't our telescope see a flash of light?
You would think so. But this is where the physics forces them into a very different strategy. It's the difference between broadcasting and narrowcasting.
Broadcasting is like a radio tower, sending the signal out in all directions.
Omnidirectional, like a light bulb. Anyone can see it. But quantum signals, they generally must be narrowcast, like a laser pointer.
Yeah, why? Is it just to save energy?
It's a hard physics constraint. It all comes down to something we call the 50% requirement.
Okay.
To successfully reconstruct quantum information, to actually read the message, the receiver has to catch more than 50% of the photons that were sent.
Wait, hold on. More than 50%? That seems incredibly high.
It is. In classical radio, if you catch a tiny fraction of the signal, maybe 1%, you can still hear the music. It might be staticky, but you can amplify it, clean it up.
Right.
With quantum information, if you don't catch the majority of the particles, the information isn't just fuzzy, it is mathematically lost. You cannot reconstruct the state.
So you can't just spray photons into the void and hope someone catches a few?
No. You have to aim them directly at the receiver's bucket. If you lose too many photons to interstellar dust, or just because the beam spread out, the message is gone. It doesn't arrive as a bad signal, it just fails. It dissolves into noise.
That changes everything. It means you have to know exactly where the receiver is.
And crucially, it means the receiver needs a very, very big bucket.
Which brings us to the hardware gap. And I think this is the part of this deep dive that really blew my mind. What kind of equipment do we need to tap in?
Well, it's not the Hubble. Think bigger.
The James Webb.
Much, much bigger. The physics tells us that the size of the telescope scales with distance. To do this with Alpha Centauri, again, our nearest neighbor, the easiest target, you would need a telescope approximately 100 kilometers wide.
100 kilometers. That's the size of a small state.
It is roughly the size of Delaware. Or imagine a lens that stretches from London to Oxford, floating in space.
That's insane. We're so proud of the James Webb telescope, and that's, what, 6.5 meters wide?
Exactly. We are bringing a thimble to a fire hose.
Now, hold on. Let me play devil's advocate. We have things like the Very Large Array in New Mexico, right, where the dishes are spread out over miles. Can't we just do that?
That is a great question, and it's a common misconception. The VLA uses something called interferometry to get a sharper image, better resolution. They're essentially using math to simulate a bigger lens.
So why can't we do that for quantum signals?
Because here, we don't care about resolution. We care about collection. We need to physically catch the particles. If you have two dishes 5 miles apart, all the photons hitting the ground between them are lost.
And if you lose them?
You break the 50% rule. The message dissolves. So you can't have a few dishes spread out. You need a solid, continuous bucket to catch every single drop.
A solid bucket 100 kilometers wide. And we definitely do not have that.
We absolutely do not. We are currently incapable of receiving the call.
So let's connect the dots back to the Fermi paradox. If we apply this quantum theory, the silence actually starts to look like a technical inevitability.
It really does. It gives us a few very plausible scenarios.
Okay, let's walk through them. Scenario 1, the missed connection.
Right. Alien civilizations are using narrowcast quantum beams. Because those beams are so tightly focused, they aren't hitting Earth. They're whizzing past us in the dark. We are simply not in the line of fire.
Like a laser pointer aimed at a friend across a stadium. The people in the other seats won't even see the light.
Exactly. Unless you're the target, you see nothing.
Okay. Scenario 2, the leaky bucket. This is where a beam does hit Earth.
Maybe by accident or a probe trying to ping us. But because our telescopes are tiny, a few meters, not 100 kilometers, we don't catch 50% of the photons.
So what happens then? Do we see a glitch?
We might detect a few stray photons, but without the majority, we can't decode the quantum state. To our instruments, it would just look like random noise, background radiation.
Yeah.
We'd filter it out as static and move on.
That is so frustrating. The answer to, are we alone, could be sitting in our data logs right now, just labeled as noise.
It's entirely possible.
But scenario 3, this is the one that really got me, the do not disturb sign.
Or maybe incompatible hardware. Think about it. Any civilization advanced enough to build a galaxy-spanning quantum network has to have incredibly powerful telescopes.
Of course, they have the 100-kilometer scopes. They can see us.
They can look at Earth. They can map our cities. And they can look at our orbit and see very clearly that we do not have a 100-kilometer receiver up there.
They know we can't hear them.
They know that sending a quantum message to Earth is futile, a waste of energy. It's like trying to airdrop a file to a telegraph machine.
You don't get mad, you just realize the hardware isn't there yet. So they don't bother.
They simply don't bother trying. They're waiting for us to upgrade our hardware.
That flips the whole dark forest theory on its head. It's not that they're hiding because they're afraid, it's that they're just waiting.
Waiting for us to grow up, to build the bucket big enough to catch the rain.
That is humbling. We're sitting here wondering why no one is talking to us, and they're looking at us thinking, well, call us when you install a landline.
Essentially, yes. The silence isn't proof of absence. It's proof of our own technological immaturity.
So does this theory solve the Fermi paradox? Can we pack it up?
Kind of.
Kind of.
Well, it explains why we don't detect their primary communications. But it leaves a few open questions.
Like,
The obvious one is, if they know we're here, why not just use dumb radio waves to say hello? Just a simple beep beep to let the primitives know they aren't alone.
yeah, that seems like common courtesy. We come in peace, sent via AM radio.
Or why not physically visit? But those are questions about, alien psychology or sociology, not physics. The physics just tells us that if they're using the most efficient methods, we're deaf to them.
It's a fascinating perspective shift. We assume that if aliens existed, they'd be desperate to talk to us. This theory suggests we might just be disconnected.
We're offline in a connected galaxy.
So what does this mean for us? Should we start building a 100-kilometer telescope?
Well, the engineering challenges are massive. But it does suggest that our search for extraterrestrial intelligence needs to evolve. We need to stop looking for radio beacons and start thinking about how to catch quantum states.
It's amazing to think about. We usually picture the silent universe as this empty, lonely place.
But if this is true, the silence isn't empty. It's dense.
I love that. The silence isn't empty.
It's full of information we just haven't learned how to read yet.
Well, that is a lot to process. We've gone from the crushing loneliness of the Fermi paradox to the idea that we're just missing the login for the cosmic Wi-Fi.
I'm waiting for the hardware upgrade.
Exactly. I want to leave you with a thought. We've been talking about how we can't hear them, but imagine the moment we finally flip the switch on that 100-kilometer telescope.
It wouldn't just be a stray beep.
No, we wouldn't just be hearing a hello. We would be plugging into a network that's been running for potentially millions of years. A universe buzzing with high-speed, encrypted quantum conversations crisscrossing the galaxy. A bustling cosmic internet happening right now, passing through us, invisible and silent, just waiting for us to get smart enough to log in.
We aren't alone. We're just disconnected.
And that is a hopeful thought. Thanks for listening to this deep dive. Stay curious and keep looking up.